So, hi, I'm the new one. My name is Keyvi. I'm a key value index. I'm based on Finite State. If you don't know what Finite State means, doesn't matter. I think I will show it during the talk. I'm an open source project, not even a year old. So first, who's using Keyvi? And I'm working for Cliqz, and probably also you probably don't really know us. We are building a browser with anti-tracking technology as well as integrated search. So, and Keyvi is part of the search engine, and yeah, I mean, please install us. Okay, search engine-wise, let's look into the numbers. We have like 1.8 billion URLs indexed. I roughly counted, took a long time, 13 billion data points, key value pairs. Our index size is around 2.5 terabytes. That number has to be a little bit put into context, and you will later see why. We have like a 60 milliseconds average latency, and as you might have seen in the browser, what we do is we do search as you type. So you're not putting in the query, press enter, get the search result, but we search while you are typing. Right now, we get something like 6,000 requests per minute. We are able to do more, so yeah. And everything works actually quite fine with 99% availability. So why did we build it? And why didn't we choose something else? So that means that we have to a little bit look into the history. And we started actually quite the normal approach. If you're building a search engine, okay, let's take Elasticsearch. Actually, this didn't really work quite well for our use case. This is more to the fact that we are not doing a classical full-text search, but rather that we do it a little different. And so the reason for like abandon Elasticsearch was because it didn't fit our model. So actually our model fit more to something like a key value store, and we switched to Redis, and we were super amazed about it. It's great. It's simple. It's space efficient. And what we also loved is these, if you know Redis, these server-side scripting stuff. So you can run Lua scripts on server-side. So you're already reducing your search result on your node in the cluster before sending it back. Saves a lot of time. We know that networking is one of the biggest bottlenecks. Still, Redis was also not best. With more users, we run actually into capacity problems. The first capacity problem we hit was space, so the size. And when I showed you the 2.5 terabytes in one of the first slides, actually when we decommissioned Redis, our index size was 5 terabytes. And with Keyvi, we reduced it to 2 terabytes. If you a little bit know, like we run on AWS, if you a little bit know the prices there, you can calculate yourself how much money that means. Still, so one capacity problem was actually to get enough machines. The other thing is if you are getting a large machine, because everything, I mean, might not have been clear yet. If we do this 60 millisecond search, we actually have to serve everything from memory, right? So if you're getting a large machine in Amazon, you're also getting a lot of CPUs. Doesn't really fit with Redis, because Redis is single-threaded. And I think like 90% of Redis users don't hit this problem, but we hit it hard. The reasons why it's single-threaded is also because everything is on the heap of the process, which makes it also quite risky, because if this process dies, you lost it. And actually, it takes quite some time to reload the stuff. So that's why Keyvi came in. And first of all, it was a massive size reduction. second, it's multi-threaded, so we can do it with many processes. And the reason for this multi-threading is because it's using shared memory, so memory mapping, basically. And last but not least, due to this memory mapping, it's also more reliable because, well, when a process dies, it dies. You have other processes, no problem. If you reload things, it's cached in the OS, it's quickly there. So, and to give you a little bit more reasoning here is like a very simple size comparison between Redis and Keyvi. Yeah, I mean, the first thing you see on this slide is, okay, Keyvi is smaller, great. If you look a little bit deeper into the numbers, you actually see it's not linear, right? That's interesting. It's like 1 million pairs, 10 million pairs is 10 times more than 1 million. 100 million is 10 times more than 10 million. You see that for Redis. For Keyvi, it's kind of interesting. This is not linear. It's sublinear. And when I explain this finite state thing, you probably will get why. Still, this is not the 60% space savings that I claimed in the beginning. So actually, space savings is based on your data. And I print here a little bit the compression ratios that you can get with Keyvi. I mean, if you know Redis is a hash table. It doesn't matter what you put in from like a space perspective. For Keyvi, it actually makes a big difference. So something like a term dictionary, okay. Then we have like content, which was the previous kind of benchmark. Content is something like, okay, you have the text of the page and so on. If you just have filtering, that is like a list of domains which you want to blacklist because they are adult content or you know that they lead to 404s or something like that. And the most compression you get with scores. With scores, I mean something like statistical models. So basically numbers, something that you have in your model, some ranking features basically. And okay, we saw the space. Now let's look at the lookup benchmarks. I try to make it visible. I mean, it's always hard. Actually, it's always hard to do benchmarks, and you'd always do it wrong. And the other thing is with doing these kind of benchmarks is, do you measure the store or do you measure your network? Actually, most of the time you measure your network and not the store. Still, you can see some stuff here. We see that if I try to make a kind of a fair comparison, I put Keyvi into a single-threaded mode as Redis, and then just compare the one that's just the blue and the yellow one. We see it's kind of on pair. It is a little bit worse. Maybe I have to tell a little bit on what chunk size means. If you know Redis, you have something like called a Redis pipeline. So actually, you are not doing one lookup at a time. That would be bad because you would just spend time for your networking. You would like lose all your performance in RPC. So what you do is you collect what you want to know, send it over the network, and then get 10, 20, or 10, 50, 100, 200 entries in one step. And that's what this chunk size means. So there's even a little problem with Keyvi, it seems, on this 10, chunk size 10. But if we are now putting it into multi-threaded mode, it clearly outperforms Redis. And also the other thing is, what if we are not doing IPC? Which we don't have to because it's shared memory. I will explain a little bit more go a bit into detail later for this no IPC case. But this is just to give you a little bit on an idea what, because when you do these kind of benchmarks, you have to see what is the cost of the actual lookup and what is aside from that IPC, RPC, stuff like that. This benchmark was also only on a local machine because what I'm not interested in here is on the network. Of course, on the network it looks even completely different. So let's a little bit look into how this thing works. And this is a quite super complicated picture, but this is the way it is, right? You have a couple of workers on one side, and you have a cluster full of machines on the other side. What I haven't told you, actually, we would not put one Redis on one machine, but we would use several Redises. I mean, that's how you scale out Redis. You just start several ones. And then you have, instead of single-threaded, you have then, I don't know, 5 threads, because you started 5 Redis servers. Still, this is a bit complicated. Let's zoom a little bit into this. Just look at one machine. So you have a couple of Redis servers. Okay. Still, the data is everywhere on the heap of this process. Data access is local, so that means I cannot, from one Redis server, I cannot access to the other. This is for some applications. Actually, in our search case, this is a problem, because sometimes you want to have access, or some ranking data you always need, right? And you can't do that. So what you have to do deep copies. You have to put it on every Redis server. Then your size will go up again. If one of these Redis servers dies, it has to be reloaded. And in our use case, we had times like 40 minutes. And that's pretty bad. I mean, you don't want to have 40 minutes downtime. So how would it look in Keyvi? Well, as I said before, it's shared memory. So instead of dividing it into 5 pieces, if I would have 5 Redis servers before, I would now have just one piece on one machine with shared memory. I can start as many processes as I want. If it crashes, no problem. You have enough workers. You just start a new one. I mean, we actually use multiple processes, not multiple threads. So that's a little bit more robust. And the other benefit of this whole thing, which I haven't touched upon yet, is if Redis loads something, you have to deserialize it. So it takes these 40 minutes, I told you. On Keyvi, this is just put into memory, and that's it. So there's no deserialization time. So instead of these 40 minutes downtime, you have 0 minutes downtime. Because of this shared memory, you actually could argue, like, why do I need a server architecture at all? Actually, on the local machine, I mean, I can just load it, right? And you can do that. And because we traditionally started from replacing Redis with Keyvi, we actually haven't really thought about this use case, but we later realized that actually Redis is completely an in-memory store, but Keyvi actually isn't. Because it's shared memory, you put it into virtual memory of the operating system, so you can have even a bigger index than the size of your RAM on the machine. So this is an example. We have like an index size of 2 terabytes putting on one machine, which has like 250 gigs of RAM. So it's almost like 10. You have like 10 times more index than on the than you can store on RAM. And what the OS is doing is like paging the whole thing, right? This is compared to a setup we have right now. It's like, okay, the alternative is having 10 machines with sharded data, and the alternative is the putting everything on SSD. So basically, you have in the 2 upper scenarios, you have the network I/O. On the 2 lower scenarios, you have the disk I/O. And what we are comparing here is a little bit like disk I/O versus network I/O. And this whole SSD case, really, on rotational list, forget it. But with SSDs, is actually quite an interesting case because it completely changes the picture. So you see, like, okay, on a cold run, it quite takes some time. So cold run means you have nothing in your RAM, you just freshly load it. But once something is loaded, and actually in the test we are loading, it's also doing some I/O. It's not completely without paging. We see that it actually works quite well on SSD. This is something we are working on. It's not quite clear yet. Okay, so I think now you should know why. And now I want to tell you a little bit about the how. And now I also like look into what again was this what finite state something. So this is actually it's not a finite state transducer. If you correctly, it's finite state automaton. I just put like 4 words into it for you: Berlin, buzzwords, Sparse keywords, and some of you know that. For some of you, it just looks a bit similar to something that you know, and probably you know this one, which is a trie data structure. So what's the difference is just that, okay, this one has a little less circles, right? This is like kind of obvious, there's a little less circles. What we do in a trie, we compress prefixes. In the state transducer, we also compress suffixes. You see that keywords and buzzwords actually share the same suffix. It's a little bit hard to always explain this on such a small example, but as I showed you before with the compression ratios, it quite matters. And it's also it's different on what kind of data you put in. Okay, how do we build this thing? We have big data, right? We have like terabytes of data. So obviously this whole thing doesn't fit into memory. I mean, that should be immediately clear. What does it mean for us? Well, if we want to construct such a state, we have to actually know all the outgoing transitions. Simple solution, we just sort up front. Sorting, we all learned it in your university, some external sort, it's a solved problem. What we in addition have to do is we have to find these ways to optimize this thing, the so-called minimization. And what you can do here is just use a hash table. This has you're getting back to this problem of everything in memory, so your hash table should be quite efficient. The other thing is, and I'm not making an academic career with that statement, is we make the hash table bounded. That means that the finite state machine will not be minimal. This is horrible for academics. But in practice, this is like saves you. And what Keyvi also applies is an LRU algorithm, so least recently used. We just push the states in the hash table up, which have been minimized, and we throw away the ones which don't minimize. And in the end, we somehow have to stream input and output. So I'm not sure if there are some Lucene folks here, but you know this kind of thing, right? Lucene has this, right? They have finite state transducers deep in Lucene somewhere. And we can a little bit compare Keyvi and the Lucene implementation. And okay, we have to somehow solve the persistence problem. So what we need is some kind of clever bit logic. And this Lucene is also doing it quite clever. Basically, what Lucene does, it persists a node as small as possible as some kind of bit vector. The difference to Keyvi is it uses the so-called sparse array packing. And I will explain you what this sparse array packing means. So you have like say this is like your state, and we put that into some representation, into a sparse array representation. A sparse array just means, okay, you have a lot of holes in your array, so a lot of zeros. To make it efficient, we use, for the labels, we use 1 byte. Now you can say, okay, single byte encoding. We are in the year 2016. It's quite easy. Just use UTF-8, like I show here. That just means, okay, I have 3 states. Say, if I have a UTF-8 character which is 3 bytes, I just have 3 states here, which I somehow wrap into 1 state, so it looks like the same from the outside. Then we need something like, okay, every structure needs some kind of pointers, right? So we have also a vector of pointers here to connect the different states. So still okay, we can put this one after another, but that wouldn't work, right? That would not save the space. So how do we combine these? And why do we need the labels at all? So I hope this gets clear now. So given of these two of these sparse arrays, we try to combine them. And if we would, like in this case, we want to try to interleave them, that would actually mean this doesn't work. It somehow clashes on the A. Okay, next try. Clashes on the beginning. Next try. Okay, this looks almost. Again. Yeah, I think we made it. So we finally found a way to put these two things together. And it looks, in the end, it looks like that. So we combined both of these sparse array representations into one. I'm not telling you the whole story. There's obviously a little bit more, a lot of tiny tricks to make this super fast and quick. We use something like intrinsics. I told you this 2-byte thing. There's obviously some kind of variable length encoding behind the scenes. We are not using absolute offsets, but relatives offsets. So saying something like, okay, go 5 steps left or 5 steps right. We have to get the when we build the structure, we have to keep the memory requirement low, so we use something like sliding windows, and etc., etc., etc. Okay, now let's look into the lookup itself. And you might already guess it. It's quite easy. You just start from an offset. You go a little bit. You want to look up something like the E. There you find a pointer to the next one, and then you just repeat the whole thing. And now something comes from this pretty interesting in this data structure. Actually, it doesn't matter at all how many data is in there, because it only matters the length of your key. Right? As long as you can build this thing, the lookup complexity of this thing is n, which is the length of your key. Okay, so far I just showed you how to look up, and I showed you a little bit the state automaton. But we also, key value means that we also want to have values. And I can just briefly mention that and how it works in Keyvi is because that's not so much the interesting part. Is of course we need some kind of buffer where we have the values in, and we have some kind of pointer which points to that. And this is pretty much the same, independent of whether you use Keyvi or Redis. Or I mean, in the end, this part is always the same. We have types like something like key only, which would mean this filter type of things. We have something like ints, if you just need very simple things. Strings, which is actually superseded by JSON. JSON means you can store anything in there. There's something like a special subtype which is called int with inner weights. That's for a special use case where you want to, while you are looking up, go a certain path. Sounds complicated. That's exactly the completion case. You're starting with FA. And the most you want to have the most relevant completion, which would be probably Facebook, and you don't want to traverse the whole thing, but you want to have it pretty inefficient. Then for that you need something like inner weights. Of course, we are not storing JSON as is, but using some clever compression with message pack, which is a binary representation. We can put snappy, setlib, whatever on top. So I said key value index and not key value store. So what about updates and what about real time? That's obviously two questions. But I have to challenge that a bit. What is really your use case? Do you really need real time, or do you just need to have it fast enough? I think most of people just need it fast enough, right? And the same for the updates. Okay, if you have constant writes, constantly write to it, Keyvi is not for you. Use Redis, use something else. If you have mostly reads and a little bit of writes, consider it. In the end, it's the same kind of limitation or thing that you have in Lucene. And Lucene, you have these segments, and they are immutable, and then the segments get merged. We don't have that yet. What we do is the pragmatic solution of segment merging. It's just having one huge master segment, and on that we apply just delta updates. And they are not cumulative. We are just always replacing them. But on the size-wise, these delta updates are much, much smaller. And we can deploy them in a short amount of time, and depending on the use case. Some we want to update hourly, some daily, some stuff just on demand. So what I haven't told you about is what else can you do with Keyvi, because it's finite state. It's not a hash table. You have this little nice graph structure. And this finite state, some of you might know, this somehow sounds like NLP, and actually this is where it used to be used. So what you can do is, if you want, you can still build an entity recognizer. We are using it also in Spark. The other part of things is like all these approximate or completion type of matching things. There's also things like you can use it for geo applications. Because in the end, the geo lookup is just an approximate match. You are here, you want to know where the next drugstore is, so it's an approximate match in the end. All right. It's just a small project right now, but still, for more infos and material, just go to the URL there, which is right now just a redirect to a GitHub page. But what you find there is like all these more information about that, also the papers and so on, which are basically like similar. It's based on the same stuff that Lucene is based on. Yeah, and look around, and I hope maybe you have a use for it. Thank you. So I hope that there are some questions.
Thank you, Hendrik. Oh, many questions. Yeah.
Hi, I have a question about one of the first slides you show, and you have this FST with suffix compaction. Yeah. Okay.
SSD part.
FST. Finite state with machine.
This one.
This one. Yes. So you have here like buzzwords and keywords.
Yeah.
And they end up in the same state. So you can say that you have those two different words in your dictionary, okay? But how do you associate different values with?
That wouldn't work in this case.
Okay.
So this is exactly the point, that a value basically means that your end state is different, and then you would not be able to compress it. I mean, in this example, I simplified it with just showing a key-only kind of structure. In real applications, we, of course, have values, and then the picture changes. But still, if you have something like ranking data, some model data, it's the slide that I showed before, it still compresses. And it's still like, what helps Keyvi is giving it a lot of data. Because with more data, you increase the probability of some kind of duplication. In the end, you can say this is somehow a deduplication engine. More?
Yes. You mentioned Lucene has an FST in it. That's,
yeah.
But how does it compare to this one? And you mentioned you do array interleaving for compression.
Okay.
They have different compression methods, but performance-wise, memory-wise, these kind of things.
Okay. I prepared for this question.
That's why I asked.
Yeah, I mean the reason why I didn't show it, it's again my kind of questioning this benchmarking, because it's always hard to do benchmarks right, and I follow the implementation in Lucene for quite some time. I know it, but I'm not an expert on it. So what I did was I just quickly last week implemented some tools to make these kind of benchmarks. And size-wise, it's almost equal to Lucene, but I was not able to get a large, put in large data. For me, it just crashes. The memory consumption during the construction is too high. It doesn't work because it basically uses, when I showed this hash table thing, it uses something unbounded. It doesn't have these bounded hash table, for example, and that just blows up. For lookup, I did some comparison here. Because what you have in Lucene is you have every state it's not using the sparse array thing, but it puts all the outgoing transitions in this state. So what you have to do is during a lookup, you always do a linear scan in every state and have to find the right spot to continue. While you in Keyvi can do the direct, you can go directly, jump directly. So I have a benchmark here, but honestly, I'm not sure is that due to Java, is it due to C? I don't know. I don't want to start a language war. So it is something like 8 times faster in Keyvi. But I mean, if we make a proper comparison, we should compare algorithms and not implementations. And maybe it's something that Lucene folks could look into and considering taking some of the features out of Keyvi and putting it into the Lucene FST implementation.
Any
More questions?
No.
No. Thank you.